All right. So our notation, we have variables. And so alpha and beta are often used for sentences, things that are true and false, right? X's and Y's tend to be used for objects, right? And these tend to be used for things that are true or false. Right? Oh yeah, so I guess these are axiomatic variables. Well, these are bigger sentences, but the bigger sentences often to be true or false, right? And I tend to not use P and Q very much. I tend to use alpha and beta, because even if I'm writing this down, right, I could write P and Q, but then that kind of limits me to this variable and this variable, and I want the thing over on the left-hand side to, it could be a more big general sentence, right? It could have an or in it, right? So, right, it says they're both true, right? And again, this is looks like an A, right? And that's or. And another, what sometimes I remember here, you have a bucket, things are falling out, right? And is less likely true, right? Because if one of them is false, then they all fall out of the bucket, right? Well, or if any of them's true, they stay in the bucket. So I kind of remember that, but I'm always forgetting which is which. In fact, I've thought about doing a global change from that to that, because I remember this one better, right? But this is the logic one that you're supposed to use. Well, this one has an and, a more English feel to it, right? There are different ways to do negation. That's the way we're going to do it. Implies if alpha is true, then beta is true. Now, we're going to spend a lot of time on this because people have a lot of misconceptions about what it means. Right? If you're a hound dog, then you're a dog. If you're a hound, then you're a dog, right? Why? Because the set of hounds is a set of dogs, right? And so here, we're going to connect these to intersection and union, right? Because we're going to do Venn diagrams, right? Here's where alpha is true. Here's where beta is true. Here's where they're both true. Right? And here's where one of them's true. If and only if, right? That means if alpha is true, beta is true, alpha is true, right? Exclusive or, it means that either they're both true or they're both false. All right, so these are what you can write down. Yeah. So sometimes people use this, right? And that kind of says whenever this is true, this is true, and whenever this is true, this is true. The problem with this, to me, it implies that this is an object, right? Here, I would say these two objects are the same objects, right? So, all right, so now yeah. Line underneath it? Does it have a line underneath it? No, I think that the I and the S are doing this. Is that what you mean?
Like, how you said alpha, beta?
Yeah.
That the symbol looks like a C and the line underneath it.
I think it's associated with the subset of.
It's on the same line.
I'm not understanding your question. This is if and only if. What? Sorry, what's your question?
What's the sim? What's the sim?
Oh, well, I tend to write this. He was talking about making an equal sign. So you could do this. 3 lines. That's it. Yeah. Oh, yeah. Yeah. You could do this. All right. With 1 line, we're gonna do this in a minute, and it's something different. All right. Yeah. Yeah. Well, it's kind of like the implies is this 1 line, and so you just you're kind of doing both at the same time. You're kind of doing this, right? All right. So now, what's the difference between this line and this line, right? This arrow here, it's a double arrow. And the difference is that arrow doesn't belong in a sentence of logic, right? It's talking about sentences of logic, right? So if I say alpha implies beta, it's I'm outside of logic, and I'm saying that if alpha was a line, if I knew alpha was true in my universe, then I know that beta is true in my universe. It's right, it's meta, it's outside of the inner proof, right? And so it can say right, what's a proof? It's a sequence of lines where you know that if the axioms are true, then all of these things are true, right? So if alpha was a line in my proof, which I know is true, my axioms are true, then I can write beta as my next line of the proof because it kind of follows from it, right? Does that make sense? This one says, this one here talks about truth, right? And this next one talks about proofs. So we would like our proof system to be one in which if you can prove it, it's true. And if it's true, you can prove it. But if you don't know that about your proof system yet, then these are different statements. One says, if one is true in your universe and the other is true in your universe, it's talking about truth. And the next one, it's talking about your proof system, right? In my proof system, if I can prove alpha, then I can prove beta, right? Oh, here I kind of said something different. Well, here I guess I'm assuming that we have a proof system that's sound and complete, right? So this one is saying I can go from in one line to the next, and this says in many lines I can go from one. We're always going to do sound and complete proof systems, so don't get too nuanced about what I just said. All right. Maybe okay. This one. See here the difference between these two. This one really is talking about proofs, and this one's talking about truth, right? Right. This one says in our, it could be that whenever alpha is true, I mean, these are slightly nuanced differences, and let's not get into it. Yeah. I must admit, I'm introducing notation because it's the notation page, and we're not going to do this notation very much. So if you say anything in these here that you don't quite get, don't panic, because if we do it at all, it will be much later. But there is sort of a split between, given a universe, what's true and what's not true. And if something is true in every universe, then this is true. I mean, there's the topic of what's true, and there's the topic of what can you prove in your proof system, right? And it does come up because Gödel's incompleteness theorem says no proof system can prove everything that's true, right? I mean, I'm sorry for busting your bubble, but in the 40s, up into the 40s, mathematicians thought that everything that's true can be proven. And it's just not the case, right? There are things that are true in every universe that you can't prove in your proof system. So that's just this nuance here. And we're not going to spend too much time on Gödel's incompleteness theorem, so it won't matter that much. But it's good to know. I do believe that you should know that everything's not provable, right? Just as you should know about the halting problem. Everything's not computable. Everything's not provable. Yeah? This one is within our proof. It's like plus. It's a line of our language, and the others are talking meta outside of it. And I'm kind of I state that here I wrote down some difference between them, but I must admit, off the top of my head, I can't remember where they would mean different things. But it does get subtle. So, all right. So here, oh, this won't matter to you. This line won't matter quite as much because we're doing all written tests. If we were doing assignments and you were typing, then typing for all might not be on your typewriter, right? So it just says if you're typing, you can write different things, right? That's for all, that's exists, that's negation or not, right? Or implies, and then I've been using these letters because people do it in logic, but probably many of you, and even me, as we go further down the list, don't know the letters. So, right, alpha, beta, gamma, delta, omega, mu, pi, sigma, right? I mean, we can avoid some of these and goes A's and B's, right? The capital ones are sentences, right? Oh, and then this one here, capital gamma, is a set of sentences. It's usually used for our axioms. We start knowing that these things are true. Any questions about this? So if any of this, I forget all this stuff all the time. If you forget which one's mu and you don't know which on the board is mu, then holler and I'll say, oh yeah, this is the mu, right? And if you're talking to me and you say u instead of mu, I give you gold stars. Don't worry about it, right? If you want to say A and B instead of alpha and beta, I don't care, right? All right. So, oh, let me tell you something else about me. I see some people rustling. I don't care to watch, and I don't have that good sense of time. So it's your job to say, in fact, if you don't want to say it, what you do is you rustle your bags. And then I'll say, hey, what time is it? 11:15, 11:17. All right. In fact, I tend to not ask what time it is. A better question that I ask, because my math isn't always good, is I say, how much time do we got? And then you say 3 minutes. All right. So that's what we're going to do every class. And sometimes my intuition is right and sometimes it's wrong. So don't be shy to rustle your books. And then I'll say, oh, how much do I got? You say 3 minutes. All right. So I'm going to use my 3 minutes. And just to say that we're now going to define things using tables, right? This is you're evaluating plus, right? We're evaluating times. And next class, we'll switch from that to the tables, which evaluate and or and not. We can have a lot of sort of meaning for things like the imply symbol or and or nor, but when it really boils down to it, it's an operation, a Boolean operation, just like times or plus. So how do you define times and plus? You can do it just by a table, right? For every value of x and y, there's you look it up in the table and you get the output, right? So you have specific values of x and y, you plug them in, you look it in the table, and you evaluate it. And we might make a chart like this, right? For different pairs of values x and y, we can list what the equation evaluates to, right? Everybody good so far? So what are we doing? Right, I mean, so here the problem, of course, is that there are an infinite number of values of an x and y, right? So it's hard to list them all. But we also can have various rules, right? We just use there the distributive rule, right? So those are the things that we're going to do. We're going to have tables to say how you evaluate things. And luckily for us, there's only 2 values of a Boolean variable, right? True and false. But we're also going to have rules which will allow you to evaluate things. And it helps us reason about life. And all right, so here's our tables. All right, so you can see, I don't know why there's P and Q there and A and B here, but it's good enough. You have a value of P, which is true or false, and a value of Q, which is true or false. And you can see that we can fill out the table. So you probably know already that and is only true when P and Q are both true, right? While or is true when at least one of them is true, right? And not is true when the variable is false, right? And implies is the more complicated one, which we will discuss at length, right? So here you can, if you have a particular valuation, you can plug it in, and then you can see, well, now again, you have to, if you're like me, you always have to think, okay, this one's and, so this one's or, right? And here the or is true, here's an and, so this guy's false, and we evaluate like that, right? And then implies is a funny one, but we can see if the first guy's true and the second guy's false, then we get false, right? Everybody follow? Pretty straightforward. And so we can start filling out the table. And you might ask, well, how big does the table have to be? And here with 2 variables, there's only 4, right? But when you have n variables, it's 2 to the n, right? Because there's 2 choices for the first variable, and for each of those, there's 2 choices for the second and the third and the fourth, right? And if you don't know, the exponentials grow really fast, right? 2 to the 10 is already 1,000. 2 to the 20 is 1,000,000. 2 to the 30s, 1,000,000,000, right? 2 to the 40s, 1,000,000,000,000, right? So in computer science, we should switch. I hate it when it does that, all right? So we should, in computer science, anything that is exponential, we just have a rule that we don't do it, all right? So we're only going to fill out a table like this when the number of variables is at most 3. And even 3, we don't do it very often, right? And this is a little lesson here. We're going to be, we're going to be doing things where you could say, hey, we could just fill out the table, right? And if we have 3 variables and on a test you say, hey, I can answer this by making a table with 8 entries, you probably could. And my leaning is to give you very few marks for that, right? Because our goal is to learn how to do things when you have a lot of variables. And even though I have 3 variables, it's just a simple example so that we learn how to do it. I mean, I don't want to give you a problem that has 100 variables because then that would be complicated, right? So I'm going to point out which techniques I don't want you to use, because with more variables, it's exponential time, right? All right, so here's, we can plug in another example and get another, right? Here we're just doing various filling in examples. I don't know why we're doing so many examples. But you can also, this is where I talked about intuition, right? Instead of plugging it all in, once you have some meaning, you can start doing intuition. And so the first says, if the or is true, I have 2 topics, and I know at least one of them's true, right? Then does that tell me that the and's true? Not always, right? In fact, you can see here when it works out and when it doesn't, right? Versus down here, if you know the and's true, right? They're both things are true. Then is the or true? Yeah, definitely. So, so the first one is true under some assignments, but it's not what we call a tautology because it's not true under every assignment, right? Well, the second one is true under every assignment, and so we call it a tautology, right? And we're going to just sticking that in now. Oh, there you go. It's called a tautology because it's always true, right? All right, so let's just go through and think, I'm sure you know this already, but let's just warm it up again, right? There's an and, right? So if P is it's raining and Q is I'm wet, then P and Q says that I'm doing both are happening, right? And so there's our little table again. And here we can have, so you can write this table like this, right? Where you have your two variables here, or you can write it like this, where you have P and Q and you list all options, right? You can translate between the two, right? So here's all combinations. Here's the evaluation of P and Q, right? It's only true if they're both true, right? And so now here, we could do the and of as many things as you want. And like addition, you say, well, should we put in brackets here? In what order do we evaluate these? And it doesn't matter which order you put the brackets, right? It's only true if they're all true, right? There it's the same. We don't need brackets. Or is only true if it's true as long as at least one of them is true, right? You can have the or of a bunch of things, and again, you don't need brackets. Negation flips the value, as we said, implies. Now, we're all tempted to say that what implies means is that if P is true, then Q is true. And we're going to talk about that more. But when push comes to shove, it's useful to forget that intuition a little bit and remember that it's just an operation like and or, right? And the operation, that is actually wrong. So ignore this. You did not see this here because that's the wrong table. It's clearly copied from something else. So let's think about when P implies Q is false, right? It's false when if P is true and Q is false, right? Then you've broken your contract, right? So when P is true and Q is false, this is a false. But this one here should be a true, right? So if P is true, if P is false, then things are good no matter what, right? Right, so you can say P causes Q, or you could say not Q causes not P. You can say it could be, in fact, I had a partner once that was in stats, and she had a button that says, correlation doesn't mean causation, right? So it could be that they're correlated. Whenever P is true, Q happens to be false, right? But it doesn't mean that one causes the other, right? It could be that there's some other thing that causes both of them, right? But it really boils down to it's impossible for P to be true and Q to be false, right? Could be a coincidence. Oh, here we go. There's our mantra, right? Everybody good? And as I said, we're going to, right? So here's the idea. Oh, look at, suddenly it got fixed. That's good. So here's an example that if you happen to be a hound, then you're a dog, right? But if you happen to be a person, it doesn't change the fact that if you were a hound, you would be a dog, right? So this statement, if you're a hound, you're a dog, is going to be true even if you're not a hound, right? If and only if, that's the one that we had over here by mistake, right? This one is true only if both are true or both are false, right? And actually, yesterday, not yesterday, I often say yesterday when I really mean our last class, right? I said, actually, it was yesterday. I was sitting in a restaurant with my partner, and we were talking about or and how restaurants do ors differently. And I was thinking that restaurants do or with exclusive or, right? Because you can't take both, right? But the truth is they don't. They do. It's the negation of parity, right? Because if we have our true, false, if you only get one of the meals, they're happy. You can't get both, right? But let's see. Actually, but you can get neither. All right. Oh, so this is. What is this? I guess it's negation of or, right? Because or puts. No, it's the negation of and. That's what it is. This is the. Anyway, yeah. So if you negated this, you get and. This here. Oh, yeah. There we go. Yay! That was a very muddled thing there. But I was trying to think, what do restaurants do, right? And they allow you to take nut. They're not upset if you don't get anything. All right. Here we got me claiming that it's if and only if when it's really not. Exclusive or. All right, so this one here says if they're both true or if they're both false, then it's good, right? So that's kind of if and only if they have the same value. Well, this one's exclusive or. You have to have exactly one of them true, right? And then if you have the exclusive or of a lot of things, right, you can put brackets in any direction. And what it means is that an odd number of them are true, right? So everybody know that? It's a good thing to know is that parity is counting whether the number of things true is even or odd. And one thing that makes it a useful function in computer science and things is that it's really sensitive to its input, right? You give parity any input, right? You say this variable is true and this one's false, and you get some output, whether the number of set is even or odd, right? And then if you flip any one of the variables, right, then the output flips, right? Right, so it's sensitive to the variables, all right? So in Boolean algebra, if you're doing, we often do multiplication and addition mod a prime, and 2 is a nice prime. And so if you do addition mod 2, then 1 plus 0 is 1, and 0 plus 1 is 1, but 1 plus 1 is 0, right? 1 plus 1 is 2, which mod 2 is 0, right? So parity. Oh, and then if you switch, one thing that's common is, in a computer, you get the wires either have 5 volts or no volts, and that could mean true or false or 1 or 0, right? So we often associate true with 1, right? And so parity is basically addition, right? And I don't know if I say that here, but right, so this is the sum of these is 3, which is odd, so you take the mod, you get 1, right? And if you look up, you think, well, what's multiplication mod 2, right? Multiplication is and, right? Because 1 times 1 is 1, but if you have one of them is 0, then you get 0, right? All right. So, here's just what we were talking about, right? In electronic circuits, you can have the inputs are true, false, 0, 1, 5 volts, 0 volts. And so then these are the various gates that that thing gets in the way, right? And so you have the various gates, so the operations we were talking about, and you can build circuits, right? Everybody good? Any questions?